Hello class, we're going to be talking about, today we're going to be discussing fluids slash heat transfer, um, and then also a little bit of computational fluid dynamics. So I should have posted a chapter which is covered in our book, chapter 15, in our Fundamentals of Fluid Mechanics book. And the inspiration for this is basically, well, it's in our syllabus that we will be covering this portion of it, but the inspiration also comes from the project. And if you guys remember, we have if I was just going to draw, do you remember there is a flow chamber that I wanted to analyze? That's maybe the best way to do it is just show you. I'm going to show you, let's see. Oh, hold on a sec, I already have it open. So I think I ran an analysis. So I ran a fluidic analysis here for this chamber, and if I was going to go ahead and just do, if you remember from the presentation that I have inside of Beachboard, we do have we have an inlet here where the air comes in and it goes over some heat sources. The air gets heated up, hopefully to the point where we can sterilize the air, take it to 100 degrees, then it does a U-turn and comes back the other side, and on this opposite side of this heat source there is a heat lifting, there's a cooling source. This is the essential part of the thermoelectric cooler that you can find in, if you ever seen a refrigerator, a little drink cooler, something you can put in your car, plug into the cigarette lighter, that works off of a thermoelectric cooler or a Peltier cooler, and so that part cools the air back down to a breathable temperature that we can breathe it. And so, and then up here at the top, there were some fan assemblies to remove the heat from the top here as this thing gets, if it gets too hot, then we can't cool. We can't get the cooling part to work. So let's go ahead and look at this while I have it open. I'm going to go ahead and, not sure if this is going to work, but we can give it a shot. I'm going to go ahead and try to get this flow. I just ran a fluidic analysis using SolidWorks, and let's see if this even works. I guess it did fail to complete. Okay, so I thought that I had to select the insert, the face there. That's the flow trajectory. Okay. So I actually had this completed. I'm going to go ahead and post it on Beachboard, but it showed the flow path going and then going through and then on the other side. I'm going to show that on Beachboard. This software here, this is called Flow Simulator or Flow Simulation, and it's from SolidWorks. And so you all have, as Cal State Long Beach students, we have access to this, and we have a free, I have a free download code that I will go ahead and post also. Anyone that, but you need to be able to put it on a computer that can handle this. And I'm guessing most laptops nowadays, you could at least try it and see if it works. But it's basically a free CFD program, and it's fairly easy to use. And I'm going to post up a tutorial on how to use this for those of you that know how to use SolidWorks. It's a pretty easy to use simulator. And then there was another one of our students in our class told us that there is another. I think it's ANSYS has a free CFD tool as well for students. There's different ones. I wish that we had more time in the course that we can actually dedicate to learning these tools, like in a lab environment, but this is something, if you're interested in, you'll have to do on your own. Maybe there's some simple tutorials that you can follow. So for now, I'm going to go ahead and just, so I did run an analysis, but I need to rerun it again. And so let's go back to Um, Now, what we're going to be talking about today is forced convection flow. And so we've been talking, the last subject we talked about was the boundary layer. And it turns out that that the boundary layer is an important part of fluid dynamics, as it helps us dictate how much heat transfer we can have on a surface. So if I'm going to go back here, I'm going to go down to, this is inside your, this is a chapter 7 from a heat transfer book. It's not a book that you guys, you may not have this, but this is a heat transfer. You can go through these slides, and it's the same author as the fluid mechanics book, a guy named Eunice Sengel, but it's a different book. And in there, we talk about something called the heat transfer coefficient. Now that is a key parameter that we need in order to be able to determine what kind of heat transfer we're going to get from a fluid flow and a heat source. And so if I was going to go ahead and show you a little bit before we begin that, I wanted to show you a little bit so we can tie it together to what we were studying. So this here is basically a boundary layer. There's a laminar part and a turbulent part, assuming that we are going from laminar flow and then we have a transition at X critical to turbulent. And so this is very typical of flow over a plate. The boundary layer, we didn't really get too involved with the profile, but in the last homework you were able to do some problems where you're actually estimating the boundary layer as a function of X, so X along the plate. And so at least you have a little taste of what, and if you took fluid dynamics, if you took, heat transfer, you might have done some of this already, or even in your standard fluid mechanics class. So this is something, now we're not going to get, unless you're doing a computational fluid dynamics, and I'm going to just check real quick here to see if I have anything. No, I don't have that open. That's chapter 15 as we have here written on the notes. Chapter 15 of your text will have mentioning of computational fluid dynamics and how to basically essentially how to run or what a CFD program looks like when we're trying to analyze something like a heat flow problem. Now going back to the presentation, now there's a lot of parameters associated with determining heat transfer. Part of that is as you can see here, the boundary layer thickness as a function of X. I think this was something you're familiar with the homework. For laminar and then for turbulent. And you know, if you just, one takeaway from this is that in order to the boundary layer is actually the most restrictive part of the flow of heat transfer through the fluid. You have to be able, acts almost like a solid, and so you need to conduct through it. And so the thinner the boundary layer, the more heat you're going to be able to conduct. Now, at the beginning, a few weeks ago, or maybe a month ago, we went over Navier-Stokes equations. And those are the equations, those are the governing equations that give us all our velocity, pressure, type of numbers of flow going over surfaces. And from there, we can refine it enough to where we can actually just put that together with a heat transfer problem or a heat transfer solver, and then we can actually just have the problem, have the CFD analysis solve the problem for us without us having to do any calculations. We just basically give them boundary temperatures and initial velocity of the fluid coming in, and maybe a pressure as the fluid exits. Those are the things that we have to give the model, and then it just connects all the dots, runs the solver for us. And I'm going to put a tutorial on the way how I solved the air chamber for the project that we were working on. But that's not what I'm going to talk about right now. I'm talking more about heat transfer. And for that, I'm going to go back to where we started initially, and that's the heat transfer coefficient. Now, once I write this down, you'll probably be more familiar with this. But we have the equation for forced convection, or for convection in general. We have the heat rate is equal to the heat transfer coefficient times the area, the surface area, times temperature of the surface minus temperature of the fluid. And so in a general problem, for example, we have a surface like that. I'll draw in 3 dimensions. So we have a little rectangle. And now for just for better illustration, I've been having problems with this paint here, but anyway, we have flow going over the surface there. And then we also have, now we have heat. So we have Q here. So this is flow. This is airflow, for example, going over a rectangle. We got heat dissipation. So how much heat will we be able to remove is the Q here that we have in the equation. The area we're talking about is basically the area of the top surface there. That's the area of the surface. The temperature of the fluid is basically T sub F, and then the temperature of the surface, so that's also the top here, is T sub S. Now heat transfer, so the big thing here is, how do we determine that? How do we determine the heat transfer coefficient here? All right, so if I told you the heat transfer coefficient ahead of time, and if I told you the temperature of the fluid that's coming in, and if, for example, I gave you everything except maybe one missing variable here. If I gave you the amount of heat that's being dissipated here, then you would be able to calculate the temperature of the surface, for example, given a heat transfer coefficient. And you'll notice when you go into industry, this is the big question here, right? What's your assumption there? And what a lot of people do is they'll go into handbooks and things and just pull different heat transfer coefficients. So what I like to tell the students is, for a general rule of thumb, so the heat transfer coefficient is H, and the units, if we're in SI units, it's watts per meter squared, degrees C or Kelvin, doesn't matter which one. Right. So we're going to underline that. Maybe I should cross it out. I should try to underline. Right. So the general rule of thumb, what I tell students is, for so we're going to do this, and then we're going to do maybe three different conditions here. I'm trying to draw a table here. And then for the first one, so I'm going to say the condition. I'll just abbreviate condition. First one we're going to say is natural convection. So natural convection is basically, if you just had, bear with me for a second, is if you just had a rectangle like that, and again you had your heat transfer or your heat flow. So this could be another, like a chip that has internal heat generation. And what's happening is that your air, you don't have forced convection. Forced convection means that you have a fan or some kind of a pressure device, for example here on the right side, causing the fluid to flow, or air to flow. In this case, you just have standing air. So what's going to happen is the air is going to travel this way, and then it touches the hot surface and it starts to go up due to buoyancy. So your air streamlines are going to look something like that, right? They basically touch the surface and go up. So cooling by that is not as good as if we force air over it, right? But it's something, right? It's kind of Mother Nature's way of keeping things from overheating. As the air heats up, it basically rises because it drops in density, and that's called natural convection. You have to have gravity for that. So this can't occur in space, for example. If you're on an International Space Station, this won't occur. The air just kind of forms a blob up here and doesn't move. It heats up. It could heat up, but there's no gravity to kind of aid it in moving out of the way. So for natural convection, um, you'll have an H somewhere between 1 and I like to say between 10, just to keep it easy. Between 1 watt meter square Celsius to 10 watt meters square Celsius. And that just depends on just the surface here. There's certain parameters that make it go from 1 to 10. How much obstruction, if there's any, how much natural air you have coming in and coming out. Now that's for natural convection. Then we have forced convection. Oh, I forgot to mention. Um, yeah, this depends also, the heat transfer coefficient depends on, this is for air. So again, the second one, forced convection for air, we can go for anywhere between 10 to 100. And that's, you have a fan. Sometimes you can get larger than 100 if you have some fans that impinge the air, so that force the air, then the air comes to a quick stop. Stagnant flow, if you guys remember, we did some analysis on stagnant flow. I think some streamline calculations. So that's for forced convection. Now, if we replace the air with water, water has a much larger heat capacity, and it has it's a fluid that that has better heat removal properties, obviously, as you've probably experienced from getting splashed with a hose. So if someone was to put a fan in front of you, if you're hot, blowing 80-degree or 75-degree air, that's one thing. If someone throws a bucket of water on you that's 75 degrees and it's a hot day, then you're going to experience a much colder reaction, right? So that is going to go between 100 and 1,000. So for water. So this just kind of gives you an idea, a general ballpark as to so this will determine how much heat we can remove, right? So it just depends how you look at this. The heat removal is equal to the coefficient of convection coefficient times the area. So if we want to increase the heat removal, we can either we can have H go up, right? Or we can have the area, the larger area. And so everything, or we could increase the delta T here. So we know that the heat removal is basically is proportional linearly to the heat transfer coefficient of the area and the change of temperature between this hot surface and the cold air. Okay, so again, what you need to remember is this equation here. So I'm going to go ahead and I'll save this. Why not? Maybe 4/9/2020. And then we have so I told you the parameters there. Now there's different. Now how do we get how do we obtain this heat transfer coefficient? And again, this is the big question when you're out in the industry, is how did you get that number? People may ask that, and you can just say, well, I got it from a textbook. In the case, textbooks will have very simplified conditions where you have flow going over flat plates and things like that, and you'll have to do an estimate there. You can get it also from journal papers, and usually in journal papers you'll get more complicated geometries, and then you might have more, and these are all going to be, typically they're derived empirically, right? So So that means they're from tests. So there's a bunch of graduate students that go and they do a bunch of tests and they collect data and they say, well, flow over a flat plate or flow over a certain complicated geometry behaves in this way, and then they back out, they calculate a heat transfer coefficient. The other thing you can do is you can derive this from the CFD program, the computational fluid dynamics, and that involves, of course, the Navier-Stokes approximation, and then it's usually it's a finite difference program that you input the geometry and then and then it basically creates a mesh, and then it solves your problem, like I'm going to show you in my next video for how I solve the flow chamber for that one air sterilizer. So now the way I'm going to show you here is through correlation coefficients. This is and relations. And this is where you're going to run across numbers. For example, you're going to need to know what the Reynolds number is. You need to know what the Prandtl number is. And there's one important number called the Nusselt number. These are basically dimensionless coefficients that help us to determine, given a certain flow, whether it's turbulent or whether there's that has a high heat diffusion and things like that. It will help us to determine, basically, the bottom line is what we're trying to find is H. How much heat can we remove from a surface over, per unit? So again, what are the units here? The units is watt per meter squared degree C, right? So we're saying how much power in watts per meter squared per unit area per degree C can we remove from a surface? Well, it depends on these flow parameters. It depends what kind of fluid. Is it air? Is it liquid? Is it water? What's the velocity of the flow? That kind of thing. Do we have any area protrusions? Do we have fins that are coming off of the surface that increase the area? That kind of thing. So let's go ahead. Typically, if we're cooling by forced convection, we use the Nusselt number. Again, let's go ahead and say the Nusselt number here, and we're going to say that the Nusselt number is equal to, is equal to the heat transfer coefficient times the length of whatever we're trying to cool, divided by the material conductivity. So it's the conductivity. In this case, we're talking about fluid flow here. So this is the properties of the fluid. So this would be the fluid there, the thermal conductivity of the fluid. And so this is how you get, if you knew the dimensions here, if you knew the thermal conductivity of the fluid, and you were able to calculate the Nusselt number or generate it somehow, then you can solve for H, right? And this is one way of getting your H out. And then what we do is, usually we get Nusselt numbers through relations, right? That are, the Nusselt number is a function of the Reynolds number times the Prandtl number, where the Reynolds number is equal to the density times the velocity of the fluid times the length, the characteristic length of whatever we're flowing over, divided by the dynamic viscosity. And so it's basically it's inertial over viscous, inertial over viscous properties. And so it's a ratio, right? So the higher the Reynolds number, the more you're able to, the faster the flow, and the more you're likely to go into turbulence. And so it is the Nusselt number, which is a function of the heat transfer coefficient, is also a function of it's proportional to the Reynolds number, which is proportional to the Prandtl number. The Prandtl number is equal to the velocity divided by the diffusivity, the thermal diffusivity. So I'm just going to say, I'll put a little arrow here to signify velocity, and then I'm going to say thermal diffusivity. It's a textbook value for a given fluid. Okay, so now if we have all these fluid parameters and these properties, then we should be able to find, and if we're given a relationship, then we should be able to find the Nusselt number. Now, in reality, there's also coefficients here that are associated, there's exponents that are associated with the Reynolds and the Prandtl. So we're going to call the one that's associated with the Reynolds is M, and the one associated with the Prandtl is N. So in reality, we're going to have a situation where the Reynolds number is some proportional constant times the Nusselt number is equal to the proportional constant times the Reynolds number to the M times the Prandtl number to the N, right? And these values you'll get through textbooks and relations, and that's where it comes. We go back to when we talked about journal papers and textbooks, right? These are empirically derived. In other words, some grad student that's getting paid minimum wage is inside of a lab running flow versus temperature and versus pressure, and it's coming up with these relationships, coming up with these exponents that the professor then uses and makes a lot of money through publishing textbooks, and and then the grad student, what they get at the end is maybe a PhD or something. So, but these relationships, now go back here to the textbook. So this, again, this isn't from your fluid dynamics textbook. This is actually from heat transfer textbook, but this is inside the your beach board. And if it's not, I'm just going to double check and make sure I put it in there. So these, you'll have ways of calculating Nusselt numbers for many different type of situations. So here's what we were talking about. Nusselt flow over a cylinder. In this case, since it's a cylinder, it's the heat transfer times the diameter of the cylinder divided by the thermal conductivity of the fluid is equal to the proportional constant Reynolds to the M, Prandtl to the N, and they already give you an N here for the Prandtl number. What this book is saying that you can get the C, the M, and the N. You usually get them through empirical type of studies. And here is in table 7.1. If you have a circle, you have flow over a cylinder. Then, and if you have the Reynolds number going from a range of low Reynolds number to very high Reynolds number, then you'll use these different M. Prandtl number and the N as in Nancy exponent stays the same, but then the M as in Mike exponent for the Reynolds number will change, as well as the proportionality constant. And so this is how you would calculate, you would estimate your Nusselt number, and then from the Nusselt number you get the heat transfer coefficient. And again, the heat transfer coefficient is what we use to solve a problem. It's to basically to determine how, in our case, if we're doing this for the flow over a hot surface, for example, the air sterilizer, this will give us the heat transfer coefficient is what we use in the convection equation at the beginning of this lecture to determine what the temperature rise of the air over a hot surface is, for example. All right. And so you might want to go through some of this information here. And then there's also heat transfer coefficients or Nusselt numbers associated with going flow over banks, like tube banks. They don't have to be tubes, they can be solid sections that could be solid like rectangular, or they can be circular like this, and there'll be relations there too as well. So here's here we go. Depending on if you have inline pins or tubes where they're like one next to the other or they're staggered, and then depending on the Reynolds number, you will have these different, sorry, these different type of Nusselt equations. Now this one has the PRS. If you look down here, PRS is basically it's a Prandtl number evaluated at some average temperature, for example. And this is very convoluted, but there's ways of calculating the Prandtl number to give you these different, so you can do these calculations. And again, the end result is to get that Nusselt number, which you could then get a heat transfer coefficient, depending on the geometry, on what geometry you have in terms of flow direction, fluid flow, how these are spaced. That would be your L. The distance between these cylinders and things like that. And then I think that's all I wanted to show you with this. And there's associated pressure drops. You guys are probably familiar with some of these diagrams. And the pressure is a function of how much these kind of like these Moody diagrams that give us pressure as a function of Reynolds, as a function of friction, surface friction, and things like that. All right, so going back here, I'm going to go ahead and give this, I'm going to call this 2 for today. And then what else do we have left to show you? I think that's pretty much it. That is pretty much it I wanted to show you. So that'll end this lecture here. Thanks for staying tuned on this, and look forward to the lecture I'm going to give on computational fluid dynamics. Okay, goodbye.